Welcome back everyone to a session on automata theory and computability. In this session, let's learn what is context-free grammar and how to design a context-free grammar for the given context-free languages. In the previous lecture videos, we have seen what is a PDA and how to design a PDA for the given context-free languages. Similarly, it is also possible to write a context-free grammar for the context-free languages, okay, which is used for the generation of all the valid string belonging to the context-free languages. Okay. And this is very similar to that of a regular language, a regular grammar rather, where I have two alphabet symbols, that is a terminal. So I have a terminal symbol and I have a non-terminal appearing in the rules of the context-free grammar. Okay. So as let us brush up what exactly a terminal is. Terminal alphabet is nothing but alphabet symbols which contains the symbols that make up the string, right? So any valid string belonging to the language consists of only the terminal symbols used. So I can say that terminals are nothing but the alphabet symbols that appears in the string. And what about non-terminal? Non-terminal alphabet are the elements of which will function as a working symbols that will be used while the grammar is operating. And these symbols will disappear by the time the grammar finishes its job and when the string is generated. Okay, so this is about terminal and non-terminal. Now, if we have to formally look into the definition of context-free grammar, then context-free grammar is a quadruple, which means it is made up of 4 tuples, which can be represented as V, sigma, R, and S. Okay, so where V is nothing but set of non-terminals and terminals. So in other words, I can say that V is a set of all the symbols that is that appears in the rules of the context-free grammar. Then I have sigma. Sigma, as previously said, it's nothing but the set of terminals used. Okay, so this is nothing but the set of terminals or the alphabet symbols that appears in the valid string of the context-free languages. And more importantly, rule set. So this will contain all the rules what we write for the context-free grammar, set of rules. And finally, S is nothing but the starting non-terminal. So starting alphabet symbol. Starting, I can say that it is a starting non-terminal. Okay. These are the 4 tuples again is used in constructing a regular grammar, right? And the only difference here is with the rule section. So while writing a rule, we have to follow 2 important points. One is rules. Of course, rules will have a left hand side and a right hand side, isn't it? So I have left, and this is how the rules is written. And in our rules, we will encounter terminals and non-terminals. So what are the conditions of writing a rules in context-free grammar is left hand side should contain a single non-terminal. Okay, so it should be a single non-terminal, and I should have a right hand side. So this basically this can be anything or any combination of terminal and non-terminal. Okay, so this is about the rules, constraint of writing a rules in context-free grammar. to get a better understanding, let us take some examples which are valid and invalid according to the constraint of writing a rules in context-free grammar. As you can see on the screen, right side of the screen, I have listed few valid rules in the context-free grammar and some invalid rules in the context-free grammar. So if let us examine each one of these. See here, the first one, I'm referring to this, S gives A, S, B, right? So I have a single non-terminal on the left-hand side of the rule, and as mentioned here in the constraint, right-hand side can be any combination of terminal and non-terminal, right? So it can be anything. So this is totally valid. Even this is valid where S gives epsilon, and a single non-terminal giving a single non-terminal is also valid as per the constraints. And finally, here a single non-terminal is giving a combination of terminal and non-terminal on the right hand side. So even this is totally fine, right? When looking into the invalid examples, see here the first one is not accepted because the left hand side of the rule is having two non-terminals, right, which violates the constraint of writing the rules in context-free grammar. So this is totally invalid. And here the second one, very clearly visible that on the left hand side I have a terminal. So terminal is not supposed to appear in the left hand side of the rule, right? So even this is not valid. And final one, epsilon giving a single terminal where epsilon is not supposed to appear on the left hand side of the context-free grammar. So these three are some of the example of invalid context-free grammar, and the above mentioned examples are valid as per the constraint of writing a rules in context-free grammar. So with this, let us solve few problems. Let us write a context-free grammar for the context-free languages. Let us consider few examples. In this example, the language L is made up of string W from the alphabet symbols, which happens to be opening and closing bracket, and the definition of the language says parentheses are balanced, right? Okay. So I should consider two constraints here. One is I should have equal number of opening and closing bracket. That is one constraint. And the other constraint is I should not encounter the closing bracket before encountering its respective opening bracket, right? So it comes in a pair. Opening and closing bracket comes in a pair. So I should encounter the opening bracket before I encounter its respective closing bracket. So considering these two constraints, I need to design the context-free grammar. Okay. So this is a typical scenario what we encounter in writing a program, right? Where I need to encounter equal number of opening and closing brackets, and all the opening brackets should be encountered before I encounter the closing bracket. Okay. So I should write the grammar. Let me write the rules for the grammar. I should always start with the non-terminal on the left hand side, which is yes. Okay. And which is the simplest string that is accepted, that is epsilon, right? So if I encounter epsilon, then it has zero occurrence of opening and closing bracket, which is valid as per the definition of the language. So yes can give epsilons, right? So this is one rule. And what about opening and closing bracket, something like this, or opening brackets, all the opening brackets are encountered before closing brackets. So this is also valid, isn't it? So this can be dealt by writing the rule as S gives opening bracket, yes, and closing bracket. Okay. So S is repeated here, and ultimately I can evaluate this S to epsilon. We'll get a clear idea once I show the derivation of valid string from the grammar. Okay. Okay. And finally, something like this, like I encounter opening and closing bracket, then I again encounter an opening, a separate opening and closing bracket. So what about this one? Even this has to be dealt, right? So I need to write a grammar. So this can be written as SQs SS. Okay. So using these three rules, I should be able to generate all the valid string of, as per the definition of the language. Okay. So let us now let us see the derivation part. And what are the non-terminals used in my grammar? Non-terminals are used is only one, that is yes, and the terminals are obviously opening and closing bracket. Okay. Now, first example, what if I encounter epsilon? Is it valid? Yes. Okay, so can I derive this epsilon from my rule set? Yes. So which is that derivation? S gives epsilon, right? So this is the derivation what I write here, and which rule is applied? S gives epsilon. So when I write a derivation, I make use of two lines in my arrow marks. Okay, so this is the rule applied for my derivation. Okay, so yes, so this can be very easily generated. What about opening and closing bracket? Okay, so this also can be generated, but I have to apply a rule. S gives opening, yes, closing bracket. And what are the rule applied? The rule applied is S gives opening, yes, closing bracket. Okay, so this yes again need to be evaluated, right? So when I derive at the end, I should not have any non-terminal in my string, right? So this yes can be derived to epsilon. So when if I evaluate it to epsilon, what do I get? This is what I get. And what is the rule applied? Rule applied is S gives epsilon, right? So this yes what I'm talking about is substituted to epsilon as per my rule, whatever the rule I have written here. So I got this. Even this can be very easily obtained, right? Okay, now let me take, what about this one? Okay, I have two opening brackets followed by closing bracket. So in this case, I need to write this rule, okay, and the rule evaluated is, or the rule used is this, okay, and this S again will be replaced. This S has to be replaced. So which rule I have to apply? Among the three, I have to apply the second one. Okay, the rule applied is S gives, and finally the S here has to be evaluated to epsilon. So this is what I get, right? So I'll be able to generate this, and the rule applied is S gives epsilon. Yes. Okay. Now what about opening and closing bracket? That is a third type of string. What about this one? Okay, so even this can be very easily evaluated. S gives SS, right? Okay, and rule applied is S gives SS. This is, so what I'm doing is leftmost derivation. So in my rule, I am going to evaluate the leftmost non-terminal. So it is called as leftmost derivation, which we will be looking in detail in the upcoming video. Okay, so what I will do, I will replace this S with opening S bracket. Okay, so which rule is applied? This rule is applied. Okay, and this S is evaluated to epsilon. So what do I get? I get this. Okay, rule applied is S gives epsilon. Okay, now only one S is left here, which can be replaced as, by applying the rule opening S closing bracket. And finally, what do I get? I get this. If I evaluate this S as, I'll get the required string if I evaluate this S as epsilon. So S gives epsilon, right? So very easily I was able to generate this string. Okay, so if you take any possible combination, which I'll leave as an exercise for you. So if I want to generate this, try to write the derivation steps, try to apply the rules, and you should be able to make use of the right proper rule to derive this valid string, right? This will be left as an exercise. Okay, so for this particular problem, we have seen the derivation. Now finally, let me write the tuples value. Okay, to write the tuples value, let me clear this example. Okay, yeah, so we have 4 tuples starting with V. What does V stands for? V is nothing but a set of terminal and non-terminal, which is nothing but S, which is the non-terminal. Opening brackets and closing bracket is the terminals used, right? Okay, coming to the next one, sigma, obviously it is opening and closing bracket, which are the symbols used in my string. Then comes rule set R, okay, which is nothing but the set of rules what we have written here. So what are the rules? SQs, epsilon, SQs, and finally SQs, SS. So these are the rules what we have in our grammar, right? Okay, finally I have S, which is the starting non-terminal, and what did we use? We made use S itself, right? So these are the tuples value for my PD, for my context-free grammar. Okay, yes. So this is how we write a context-free grammar, by considering the valid string, such that the grammar should be able to generate all the valid string and only valid string, right? Okay, so keeping this in mind, we'll solve few more problems in the next session. I'll see you in the next one.